The nitriding process consists of adding a thin layer of nitrogen on the surface of certain materials. This process is made by setting out the corresponding machinery parts into a wafer, which then are set to conditions where plasma is formed. The generation of plasma is the one responsible for the etching of the material. As we see, nitrogen in its plasma state turns a bright purple color. The pieces which were set on the wafer now have the next improved characteristics: wear resistance, corrosion resistance, fatigue strength, lower friction coefficient, surface hardness. In this example, we see a 2 to the third factorial design that is used to develop a nitride etch process on a single wafer plasma etching tool. The design factors are the gap between the electrodes, the gas flow, and the RF power applied to the cathode. Each factor is run at two levels, and the design is replicated twice. The response variable is the etch rate for silicon nitride, measured in Armstrong over meter. The etch rate data are shown in the table 6.4 on the book, and the design is shown geometrically in figure 6.6. Here's the problem stated before. Here we can see the coded variables, -1 and 1 for the factors A, B, and C. Here are the two replicates. For the generation of this problem, we add up the two replicates into one to be able to generate the Yates algorithm. The Yates algorithm is displayed in here. We made the Yates algorithm to generate the contrast, which can lead to the generation of the estimates and the sum of squares for the generation of the ANOVA. The ANOVA is displayed as we can see in here. The ones that are rejected in the ANOVA are the factors A, the factor C, and the interaction between the factors A and C. This making them the significance figures. Now that we have this, we proceed by making the regression equation. The first term is the average of all the data displayed here, all the two replicates. The next one is 1/2 the estimate of the A factor. The second one is 1/2 of the estimate of the C factor, and the third one is also 1/2 of the estimate of the interaction of the A and C factors. Here's the data that I obtained by making the residual test. Plotting the residual test against the probability factor generates this plot. It follows a normal tendency. I made the same procedure for the second replicate. Here is the same regression equation. Here is the data, and here is the second plot. Checking for dispersion, I followed this attempt, the one of generating the graph using the variances of the several factors, +1, +1, and -1. We can see that the ones that are generating the most of the dispersion are the A factor and the C factor as well. For the diminution of the dispersion, we have to choose for 1+ for A factor and -1 for the C factors. Also, analyzing the plots, we can see that actually choosing the -1 will generate a bigger yield for A, though we still have to maintain our decision to get the +1. The one that gives us a better yield is +1, but we have to still keep our decision of maintaining on minus 1. And for B, we can see that there is not significant interaction between them. So in here, for a better yield, we have to get plus 1 factor. Here's a contour plot. The contour plot have to be shown in this way for us to be actually able to see the tendencies that they are following. We can see some lines that are curved in this place. The formation of these lines comes from the very nature of our regression equation, which has within the interaction of the first two factors. For the case of the natural, we follow a matrix approach to generate the factors. In this case, this is a procedure that we made, and we obtained that the betas, we found that the betas are this, beta 0 is this one, beta 1 is this one, and beta 2 is this one. And also, we get here the regression equation. We can see that the probability plots of the normality tests are pretty similar than the ones that we generated before.